That's something like yeah. It's over. But besides, like, I think there's
Okay, page 3 in your packet. Okay, so I think this will be fast because we're just going to practice applying the integral rule e to the x, e to the u du, and then identify the u value. Then we're just trying to make it fit into a rule that's available to us. So if we recall from first semester, the derivative of e to the u, which is e to the u times u prime, right? So it stands to reason that if I want to take the antiderivative of e to the u, then integral of e to the u will bring me back to e to the u. Right? So there's my rule here. So because the derivative of e is the same as the original function, the integral is also the same. Right? The only thing we got to keep track of is that if there's a u value, then the u value could produce something that we got to make sure we keep track of. So number 1, find the integral of e to the 3x plus 1 dx. Looks like this can fit into that e to the u rule if we let the exponent be the u value. Right? So u substitution. And the hope is that we can make it look like this. If we can make it look like this, then we have a rule that we can apply. Okay, so u value is 3x plus 1. That's right. In this case, the exponent is the u value because we're anticipating that we can make it look like this rule to apply for after u substitution. Okay, what's our derivative? Cross multiply. Okay, we make our substitution. Sorry, I forgot to underline to show that this is what I'm trying to do here. Integral of e to the u times du over 3. We do want to push out what? Yeah, as what? 1/3. As 1/3. Are there any x's left over? No, that's a good sign, right? That's nothing to cancel out. And we get a perfect match with the rule that we want to use. You know, we can cover up the coefficient and it should look exactly like the rule that we want to use. Okay, so we apply our integral rule. Integral of e to the u is just what? Just e to the u plus c, right? The integral notation drops out, du drops out, the 1/3 stays. So we took our antiderivative. And our final thing to do is what? Yeah, replace the u back in terms of x. I just want to connect this with first semester as well. if this was our starting problem from first semester, and if I asked you to find the derivative, the derivative of e to the u is e to the u times u prime. So it's e to 3x times plus 1 times 3. The 3 and 1/3 cancels out. This will take us back to this, right? So this is the derivative of this. It's just this semester we're starting at the derivative level, trying to make our way back up to the function level. All right, example 2. Integral of cosine of x e to the sine of x dx. There is no rule that can match this complex of a problem, right? We can't say, okay, integral cosine, integral e, we can do those. Those are not separate because they're being multiplied here. So u substitution, right? What could be our u value? And do we anticipate this cosine to go away on its own later? Yeah, because the derivative of sine is cosine, so that should work out. Du dx equals with, yeah, derivative is cosine, cross multiply. Okay, so just like what we expected, the cosine goes away, no coefficients to keep track of. We're just left with e to the u, which is a nice, easy rule for us to apply. Okay, example 3, too many terms below, we can't expand. We have to go to u substitution. What could be our u value? You have to guess. Yeah, it's never just x, right? Remember, u is always more than just x.
Yeah.
More than that.
2 plus e to
2 plus e to the x. This is not always. This is kind of like a more general rule. If you're choosing between numerator and denominator, chances are the denominator is going to be the u value because the numerator is easier to cancel out. I mean, there's exceptions to that rule. Natural log is an exception to that rule, but for the most part, if we leave the numerator alone, that usually should cancel out down the road. All right, so we do want the u to be a rather significant portion of the problem. We don't want to just let it be e to the x. So the 2 plus e to the x is a better fit there. Okay, derivative, du over dx. All right, 2 becomes 0. E to the x becomes, yeah, because the derivative of e to the u is e to the u times u prime. So the derivative of e to the x is just e to the x times 1. The 1 drops out, so it's just e to the x. Cross multiply. All right, make your substitutions. All right, just like we wanted, the e to the x cancels out, but looks like we have a different rule here, right? What does this rule end up matching with? Actually, this is from yesterday, right? Integral of 1 over u, 1 over u du is natural log, half the value of u plus c. then bring back your x.
You're really wondering that cancels out.
Yeah, that's right. Well, ultimately, here's the better way of saying it is that at the end of their, before you take your antiderivative, you have to make sure that your x's go away and that there's a rule that matches with what you're looking at. Right. So if you just replace x with u, you could get your problem to all be in terms of u, but if you don't have a rule that's available to you, then we don't have a rule to use. Okay, so this one we kind of have to test some options here. What could be a u value that will eventually take out all the x's and leave us with something that, where there's a rule that's available. It takes a little bit of looking ahead and maybe trial and error. But obviously we definitely need u substitution, right? There's no rule that can handle exactly with what we see in front of us. Okay, what could be our u value? What is it? Yeah, that's a little too much. If it's cosine e to the x, then derivative of cosine e to the x will be negative sine e to the x times e to the x. There's no match for that for cosine of e to the x's derivative.
Just the
Okay, which one?
the left first one.
Not the first one. Yeah, so again, sometimes parentheses can kind of give us some additional help, right? If we're choosing between something that is in parentheses versus something that's not in parentheses, chances are the one in parentheses will be the better u value. Okay. So the hope is that this will turn into cosine of u, and if we have cosine of u, we have a rule for that, and we're hoping that this leftover e to the x will be taken care of by this derivative. Okay, so let's see if it ends up working out. Okay, what's the derivative of e to the x? Yeah, e to the u times u prime, so e to the x times 1, which is just e to the x. All right, do the x's go away? Yes, that's a good sign, right? And we're left with integral of cosine of u. This is one of our original 6 trig integral rules. Do you guys remember what's the integral of cosine? Positive sign. Remember, this is the opposite one, right? We know that the derivative of sine is cosine, so therefore the antiderivative of cosine is going to be sine. I know we want to say negative because we're so used to the derivative way of doing things, but this is going to be sine of u plus c. And then bring back the x, right? All right, example 5, too complicated for for us to expand. There's too many terms below. We have to look at u substitution. What could be our u value? Yeah, entire denominator again. Okay, what's the derivative of e to the 2x? Yeah, remember the rule for e to the u is e to the u times u prime, e to the u times u prime. So there's that leftover times 2, right? And then the 1 goes to a 0, right? Okay, x's go away, but there's a leftover what? Half in front. Okay, natural log rule here. Bring back your x.
We have the rules on the review sheet, or we have to memorize all
You
the.
gotta memorize them, yeah. Same thing on the AP exam. They won't provide the derivative integral rules for you. Yeah, there's no formula sheet on the AP exam. Unless it's like a geometric shape, they'll give you, area of or volume of a sphere or things like that, but gotta know. Now, the good news is that on the AP exam, they tend to steer away from the more obscure rules. So I'll specify, what are the rules that have the highest chance of showing up, and you want to just focus on those rules, that's fine. We're gonna do a little bit more within our quizzes and tests. But these are major ones. The integral of e to the u, the integral of 1 over u du, these are major ones. These are guaranteed to show up on the AP exam. All right, example 6, too many terms in the denominator. We gotta look to u substitution. What could be our u value? Yeah, the entire denominator. It feels like this is less than the numerator. I typically want to choose the more complicated, but that 2 is just a coefficient in the numerator. We can factor that 2 out. It's not really going to impact us. And so, yeah, and we know that derivative e to the x is e to the x. So we know that some version of these 2 terms will show up and help with the numerator leftover with the derivative. All right, derivative du over dx. All right, e to the x becomes e to the x. E to the x times 1, right? What's the root of e to the negative x? Yeah, so it's e to the negative x times -1, which, like you said, you can pull the negative in front. Okay, yeah, I'll do that. Let's rewrite it. Now, you may be looking at this negative x and feeling like you want to push this down to the denominator. I wouldn't do that, because you want to kind of make it look like what you're trying to cancel out. So it makes it harder to match up if you're changing the form. So I would leave this alone. Okay, cross multiply. Okay, I'm going to make my substitutions. Okay, we're hoping that the e to the x is canceled out, but it looks like it's not. It's close, but not quite a perfect fit. Maybe I can do something with this. Do what here to make this look more like this one?
Factor.
Yeah, factor a 2 out, right? right, now I got a perfect match. 2 comes out in front. I have 1 over u du, which is again natural log. Okay, let's go to our test review packet. Let me do a full Parker motion. I was going to do this tomorrow morning for the morning health session, but I'll do it again tomorrow morning for a morning health session. But I do want us to get that full practice with the calculator again. So page 11 in your packet. All right, so let's be the problem here. An object moving along a horizontal line has v of t equals t cosine of pi t over 6 measured in inches per second from 0 to 11. Okay, so we're going to graph the velocity function. You're always using x, variable x in your calculator, so x sine of x pi over 6. Now, I like to start off with Zoom 6. It kind of just centers my graph into something that is it's basically just adjusting the window so that it goes from -10 to 10 on the x-axis and -10 to 10 on the y-axis. But also want us to understand that sometimes if they give us the bounds in terms of the x value, then we want to use it. So these are the x min and x max. This is the furthest left, furthest right. So we can go back to our window screen and adjust our x min, x max. Now, for me, I like to see a little beyond my endpoints just so that it doesn't feel like I'm missing something because something is at the edge of my graph. So on my window, I'm going to go from -1 to 12. Just like to make sure that I don't miss anything.
What do you do? Click on y equals and
Yeah, you go to y equals and you're going to type in x cosine of x pi over 6.
Did it say invalid dimension?
Okay. Make sure your x min is lower than your x max. Okay. I'll come around. Okay, some reason these are highlighted, so just go back up here and unhighlight them, hit enter. Unhighlight them. Try again.
That one, thank you.
how would you set the like
Yeah, go to window. And then you're going to set your x and x max to -11, 12. Just so you can see around the edges. Have a graph after that. And you see how this is a little getting cut off here? Yeah, we can make the y min go a little lower. So if we're going to make your y min go like y min, make it like -10 or something.
okay.
Just so that you always play with these 4 numbers to kind of adjust your whatever you want to see.
Well, that we need to adjust the max a little bit.
But that's okay,
Okay.
because well, let's see, your window, we should be going from -1 to 12. We don't have to go all the way to -11.
Yeah,
Just go from negative, so you're just gonna go a little beyond your edge.
okay.
Now, this is the velocity graph. So it says create the sideline for velocity. So we'll start at 0, 11 for our velocity sideline. And we'll pick out the x-intercept, right? X-intercepts is gonna be where our critical point is for our velocity graph. So we're going to use the second trace feature, the 0 feature here. The 0 will help us find x-intercept. So I'm going to pick a point to the left of my x-intercept. So there's my blinking cursor that's to the left of my target. I'll hit enter and then scroll to a point on the other side of my x-intercept, hit enter, and then hit enter a third time when you see the word guess. And it's going to find that x-intercept for you, 3. Okay, there's another x-intercept, so I'm going to go looking for it. Do second trace 0. Okay, scroll over to a point to the left of my x-intercept, hit enter. Scroll over to the other side, hit enter a third time. Fine. Okay, so this is the derivative graph, our velocity graph. Anything above the x-axis is positive velocity, anything below is negative velocity. So between 0 and 3, what can we say? Positive velocity. Between 3 and 9, negative velocity. Between 9 and 11, positive. Okay. We're also going to do a sign line for acceleration. Now, acceleration is the derivative of velocity, but it's also the slope of velocity, right? So now we're going to pick out the peaks and valleys, right? Just like how we would do points of inflection off of the derivative graph. So now, if you want to find the peaks and valleys, you're not going to do the 0 feature anymore. Guess what we're going to choose here? We're going to choose the max and min. Okay, so I see a relative max first. So I'm going to go to the max feature. It's going to feel like the 0 feature in the sense that we're going to pick points on either side of the target that we want, and the calculator is going to go and look for it for us. So if I choose the max feature, that means I want my calculator to find that hill for me. So I'm going to pick a point to the left of that hill. Hit enter. And then pick a point to the right of the hill. Hit enter. Hit enter a third time. 1.643. Now I see a valley of the graph. That's going to be a relative minimum, right? So I'm going to do second trace minimum feature and do the same thing. I'll pick points to the left of the minimum, pick a point to the right of the minimum, and then the calc is going to find that relative minimum for me. Yeah, good. 6.542. Okay, remember acceleration is the slope of velocity. So between 0 and 1.643, what do we see? Positive slope, so therefore positive acceleration. And this connects with concavity, right? If we're talking about concavity, we would say concave up because the slope of second derivative of the slope of the velocity or the f prime is what we want. Okay, between 1.643 and 6.542, negative slope, so therefore concave down, therefore negative acceleration. right? And then from 6.542 to 11. Part B, find the times when the object is motionless. So motionless at 3 and 9. There's also one more at 0 because this graph does hit the x-intercept at 0. So 0, 3, and 9, but not 11. 11 is an endpoint, but 11 is all the way up here. It's not an x-intercept. So t equals 0, 3, and 9 because v of t is less than 0. Oh, sorry, is equal to 0. Okay, part C, find the velocity of the object at t equals 4 seconds. So we're going to make the calculator find that velocity for us without having to plug in the t value on our own. So if we do alpha trace, select that y1 feature. If you're using an older calculator, you want to get that y1, you can go to vars, yvars, function y1. I'll leave that up on the board for the test tomorrow. And then do parentheses 4. So this is my velocity. What's the unit of measure? Meters per second. Okay.
What are you doing for the bars?
So I think yours can handle it, right? So do alpha trace. Alpha trace, you see that menu, and you can select that menu. Y1. Do you have that or no?
Oh, yeah, I see that.
Okay, yeah, so alpha trace Y1, and you can do Y1 to 4, and then it's going to plug that 4 into what you have stored under Y1, which is your velocity function.
You put on second alpha, right? Like,
No, just alpha trace. Yeah. I think, yeah, just alpha trace should be good. All right, next up, find the acceleration. So acceleration is the what of velocity? Slope or derivative, right? So derivative, we have our derivative feature, which is n deriv, so math 8. Okay, what's your unit of measure here? Yeah, meters per second squared. All right, is the object speed increasing or decreasing at t equals 4 seconds? So increasing, decreasing speed, we have to do what? Compare. Yeah, between what? Good. So here we see they're both negative. So what can we say? Speed is what? Increasing at t equals 4. I'm sorry. N deriv do math 8. Yeah, so math 8 is n deriv. Math 9 is FN. Okay, part F, find the total displacement. So displacement is just the depth interval of velocity, right? Displacement just means I'm accumulating my velocity over a period of time, and that's going to tell me how much ground I'm going to cover in that time period. So it's just a depth integral from 0 to 11. It's okay to have negative displacement. All that means is that we've traveled, or this particle has traveled 11 units to the left of where it started, or ended up 11 units to the left of where it started. Okay, so math 9, depth integral from 0 to 11 of your y1 or your VFT function, which you can have alpha trace, we'll hopefully get there. And if you're using an older calculator, you're going to do 4 arguments, y1, x, comma 0, comma 11. Okay, total distance. Total distance looks like displacement. We just need what around the velocity. Absolute value. Okay. So absolute value is math number ABS. I'll leave this up on the board. So do your math 9 first. Get that integral notation to show up. And then you'll go from 0 to 11. And then once you're inside where your velocity is going to go, you'll do math number ABS. Alpha trace. Yes. It may take a second to get there, but eventually you'll show 34 inches or 34.8.
Absolute value.
I'm sorry?
How do you get absolute
Yeah,
value?
so I'll leave this up on the board. So math number ABS. Okay, we'll skip H and I and we'll skip L. So just 2 more to go here.
Okay.
Yeah, no, yeah. So part J, look at the connection between these 3 here. You got total displacement, you got total distance, and you have finding a position, finding a location. So these are all kind of related. They all involve integral, but notice all the distinction between them. The last one is finding a physical location given a starting point. So here's the formula. Final position equals initial position plus displacement. So anytime I'm looking for a location, I need to have a location to begin with, a location that's given to me. And then I'm going to figure out how much progress am I going to make on top of that starting location to get to my final destination. So x of b equals x of a plus displacement, the integral from a to b of b of t. So if I want to find x of 11, I'm going to start at x of 0, not because it's always going to be 0, but because that's what they gave me. X of 0 plus, and then however much progress I need to make between t equals 0 to t equals 11.
How'd you get 3?
How to get 3? They tell us x of 0 equals 3, so I just made a substitution there. Okay, on the test, I'm going to ask you to show me the integral notation. You see how F, G, and J has that show integral notation. And I just want to make sure that we can distinguish between these 3. Some students get confused between these 3. So displacement is just the integral of velocity. Total distance is the integral of the absolute value of velocity. And final position or any location I'm looking for is point plus displacement. So you want to make sure, and also just point out that sometimes students get these mixed up. So just pay attention to these things. And also I'm looking for integral notation. I'm looking not only for the answer, but that you're setting up using integral notation. So put a star next to those 3, make sure you're looking over them tonight and that you can distinguish between the steps for each of those 3. All right, last one here, we'll skip L, but K is just average value theorem. Average velocity is 1 over b minus a, integral from a to b of t. So integral from 0 to 11 b of t, I already have that from above. So that's negative 10.993. I got my area component, I got my width component. Divide those 2, I get my average velocity.
Rendering L that test too.
Yeah, cross out L, yeah.
Play this geometry. Or a mean circle. Those problems could they possibly be an AP exam?
I'm sorry?
Could those problems possibly be an AP exam with the problem?
Maybe, but we can revisit them later. Let's go to page 7. There is a Riemann sums problem that I want to go over. Not because Riemann sums is hard, but because I want to make sure that we know how to do the interpretation of it. So this is page 7. Okay. Important key point. When you're applying or approximating a calculus process, derivative or integral, your units of measure will change. Okay, so let's think about derivative for a second. When we think about derivative, we associate derivative with what? Slope. And when you do slope, what operation do you do? Okay, division, right? You divide. And that's also going to apply for your units of measure, right? So if I start off with ounces per minute, and if I want to find the derivative, guess what my new unit is going to be? Ounces per minute, right? Per minute, right? So yeah, right, ounce per minute squared. But the idea is that we're dividing units, right? Okay. So I think students are pretty good with that. I think that just comes more naturally to us. But when you do an integral process, something is also changing. What do we associate integral with? What operation do we, or what algebraic or geometric thing when you think about antiderivative integrals? Area, right? And area, the easiest area formula is rectangle, length times width. So we're multiplying our values, which means that we're also multiplying our units. And so that's the key thing here. When you take the integral process, your new units is going to be the multiplication of these two. So what's ounces per minute times minutes? Just what? Just ounces. Okay. So keep in mind, derivative, your units will change. You're dividing your units. Integral, your units also change. You're multiplying your units, right? Just like how you're multiplying the area component, length and width, you're also multiplying your units together. Okay, so let's look at number 1 here. Hot water is dripping through a coffee maker, filling a large cup with coffee. The rate that water in the cup at time t is changing is given by a differentiable function. That just means a smooth curve C of t, where t is measured in minutes. Select values of C of t measured in ounces per minute are given in the table above. Okay, so the information that's given to us is ounces per minute. So at 1 minute, okay, there's no water that's being added to the coffee cup, or no water dripping out. At 1 minute, 5.1 ounces per minute, right? So this is probably the fastest that the water is being added there. 3 minutes in, it goes down to 4.2 ounces per minute. 6 minutes in, 3.3 ounces per minute. 9 minutes in, it's slow to a drip, right? This is slowest is going to be 1.2 ounces per minute. And then at 10, it speeds up a little bit. Okay. So this doesn't tell us how much water is in the coffee cup. It just tells us the rate that water is being added to the cup. So part A says interpret the meaning of C prime of 6. So C prime of 6. First off, what is this unit going to be? Good. Ounces per minute, ounces per minute squared. And so what does this mean? Sometimes students want to use the word acceleration. Okay, so acceleration is not going to fit in this context, even though it is second derivative in a sense. And also, we don't want to say rate of a rate, even though that is true. We want to kind of be more specific in terms of what it's saying. So C prime of 6 tells us how fast the rate of water added to the cup is changing. Okay, is the rate being added increasing or is the rate decreasing? So for instance, here, if I'm just looking at these numbers here, the rate that water is being added to the cup is generally decreasing, right? So the way that we want to say rate of a rate, we want to say that the rate is changing, or that the rate is decreasing, or that the rate is increasing. That's more clear in terms of earning points on AP exam. So we don't want to say rate of a rate. We don't want to say acceleration. We want to say that the rate is changing, or that the rate is increasing, or that the rate is decreasing. Okay, so those two words is what's indicating that there is a rate of a rate going on. Does that make sense? Okay, so now next part, approximate the value of C prime of 6. So we're going to use what to approximate C prime of 6? Okay. We can't do derivative, so the next best thing is find what? Right, slope, right? Does it matter which order pairs we choose? Close to it, right? So you can either use these two or these two. Let me ask you real quick, what if this was asking for C prime of 5? Then I have to use what? 6 and 3, okay. But this one, because 6 is in the table, you have a choice. You can choose these two, but if the number doesn't show up, if it lands between these numbers, then you're forced into two order pairs. Like for instance, if it was C prime of 8, then I gotta use 6 and 9, because 6 and 9 are the closest to 8. Okay. So if I do change in 1.2 minus 3.3 over 9 minus 6, then I get negative 0.7 ounces per minute squared. So then going back to what this means, we can say that at 6 minutes, the rate of water being added to the cup is decreasing at 0.7 ounces per minute squared at the 6th minute. Okay, interpret the meaning of the integral of C of t dt and indicate the unit of measure. Okay, so here, C of t is in what's C of t here? C of t, what's the unit of measure for C of t? Ounces per minute. And I think this is where I think students struggle here. When they see this, they see ounces per minute and they feel like they got to do something to ounces per minute, but something is changing, right? C of t is ounces per minute, but it's being multiplied by time. So ounces per minute times time will give me what? Ounce. Sorry, say it again. So ounces per minute times minute. Yeah, right. Cancels out. I'm just left with what? There's ounces, right? This is not ounces per minute squared. This is just ounces. Does that make sense? So remember, with derivative, you're adding rates, right? So ounces per minute becomes ounces per minute squared. But if I'm going up, ounces per minute will go back up to ounces. So anything that we interpret here has to be in terms of ounces. We don't want to be mentioning anything with ounces per minute because that's not the unit that we're talking about. So what does this mean? The integral from 1 to 10 of C of t dt, that means we're accumulating these rates of water being added. And ultimately, what this is going to tell us is that this is going to really tell us how much water has been added between the 1st and 10th minute. Right? Or the change in the amount of coffee in the cup between the 1st and 10th minute. In this case, water is being added to the cup. So this is telling us how much water, telling us how much water is being added to the cup in the 1st and 10th minute.
Consider it's like something using dirty first here.
Yeah, this is just an indication of what's really going on here. This is saying that lowercase c becomes uppercase c, and this is really indicating that this is how much water has been accumulated in the cup by the 10th minute, subtracting the amount of water in the cup in the 1st minute. If I subtract those two, I have the amount of water added between the 1st and 9th minute. And we're talking about ounces here, right? Not ounces per minute, even though you may be tempted to because you see C of t and you're thinking, okay, C of t is ounces per minute, but something is changing, right? Integral is changing it to ounces. Okay, so now the rest should be more familiar here. Approximate using two middle rectangles. So the setup are width components between 1 and 10. The width is 5 because 6 minus 1 is 5. The width here is 4 because 10 minus 6 is 4. And then the height that I want for my first middle rectangle is 4.2. And then the height of my second rectangle is 1.2. So we get 25.8 ounces, right? Not ounces per minute. This is ounces because I'm doing ounces per minute times time. So in other words, going back to part C here, what this is really telling us is saying that between the 1st and 10th minute, 25.8 ounces of water has been added to the cup. That's what that's telling us. Or approximating that. And then the last part, average value theorem. what is the average rate of water being added? Well, the 25.8 we can gather from part D. This is how much water has been added. We divide it over a period of 9 minutes, and then we get an average of 2.867 ounces per minute. Water being added per cup between the first and 10th minute. Page 8 is also good, but maybe I can do that as part of tomorrow's help session. So I'll do one of each type tomorrow morning. There are some additional problems in your packet that you can continue practice with. All right, go get your problems. Study for your test.
I the last one, just for a minute.
And the reason why we're talking about average rate of water being added, so the 25.8 is in terms of ounces. But then we're still dividing by time here,
Okay.
ounces per minute. We're back to ounces per minute. Even though the integral is indicated here, but then that dividing is changing the units again.
Not squared though, just.
That's right.
Yeah.